Okay, a few people have been having issues with question 19 in 6.3, so we're going to have a quick look at that one today. As a bit of a worked example. It's nice because it kind of mixes both this ugly version of a circle equation with needing to find tangents and things like that. So we might work all the way through from A to F. If you are fine with certain parts of it, feel free to just skip through this video to the parts you need. Okay, so it asks us to consider the circle defined by x squared plus y squared minus 6x plus 4y minus 12 equals 0, and to specify its center and radius. Okay, so I'll just go to my hovercam. Okay, so here we go. Consider the circle x squared plus y squared minus 6x plus 4y minus 12. Okay, so this is one of those cases where at the moment it's not written in the nice way that we often see circles. X minus h all squared plus y minus k all squared equals some radius squared. So we've got to get it into that format. We suspect we can get it into that format because we do have factors of x squared and y squared here. So we suspect that there's some sort of perfect square hiding in there, and our job is to use the complete the square method to turn these, the x squared and the y squared, into perfect squares. So our first step is going to be just to isolate all the x's together and all the y's together. So it's going to be x squared minus 6x. I'm going to leave a little gap because I know what I'm going to do next. Plus y squared plus 4y. Once again, I'm going to leave a little gap, and then I'm actually going to move the 12 to the other side as well, because I know 12 is going to end up being part of that radius, the constant bit on the right hand side. Okay, I'm then going to use the complete the square method, and remember the complete the square method means we take half of the coefficient of the linear x, of the non-squared x, so that's going to be negative 3, and we square it, so that becomes positive 9. Right, and now normally we can't just add on a number if we want to leave this whole thing here unchanged. So if we add 9, we've got to minus 9. But equivalent to minusing 9 on the left hand side is actually to add 9 on this side as well. That's another way of leaving this equation unchanged, is to add the factor of 9 to both sides. Okay, I'm going to do the same thing with the y. Okay, so we're going to have y squared plus 4y. I'm going to take that 4y, I'm going to halve the coefficient and get positive 2. Positive 2 squared is 4, so that's plus 4. And once again, because I'm not allowed to just do it to one side and not the other, I'm going to add 4 to both sides. The nice thing there, of course, is that that means that this thing here is now a perfect square. In fact, it's x minus 3 all squared. Okay, and of course this bit here is also a perfect square, and that's going to be x plus 2 all squared. Sorry, y plus 2 all squared. And on this side here we're going to have 12 plus 9 is 21, plus 4 makes 25. Oh, what a nice coincidence, a radius of 5, and we're done. That's in that nice format that we expect circles to come in. So its center is going to be, we're going to have a center of 3, negative 2, because it's whatever makes these brackets 0, and we're going to have a radius of 5, and then we should always, I think you should always have a little sketch off to the right where you can mark out things like that. Radius of 5 means that we go up by 5 to mark this spot here. It's going to be negative 2, takes us up to positive 3. To the left by 5, it's going to take us to negative 2, 2. Well, haven't made this sketch big enough. It's always the danger. 3, positive 3. Down here is going to be 3, negative 7, and somewhere out here we're going to have 8, negative 2, and then Let's be too careful. Oh my god. Probably one of the worst circles I've ever drawn, but that's fine. Okay, let's keep going. Part 2. Show that the point -1, 1 lies on the circle. So really all that's saying is plug in -1, 1 and see if it works. So let's plug in -1, 1 and we get x, so which is, that's -1. -1 minus 3 squared is going to be -4 squared. 1 plus 2 is going to be 3 squared. So does 4 squared plus 3 squared equal 25? 16 plus 9 equals 25. Yes, it does. Therefore, -1, 1 lies on the circle. Beautiful. Alright. Then it wants us to find the equation of the tangent drawn to the circle at the point -1, 1. Okay, so at this point here, -1, 1. At this point here, -1, 1, we're going to have a tangent just touching that circle like that. And we want to find what's the equation of that tangent line. Yep, okay, no problems. The way we find a tangent for something like that is we realize that any tangent line that we draw is going to be at right angles to our radial line. So if we can find the equation or the gradient of the line between our point and the center, then the gradient of our line is going to be perpendicular to that. So we're going to be able to use that -1 over m idea. Alright, so let's do that. So let's find, so this is part 2 of question of part B. So we go from -1, 1 to our center, which is 3, -2. That gives us a rise over run, a gradient of, the run is -1 to -2, so -3, sorry, the rise. The run is from -1 to 3, that's 4, so we get -3/4. We want the tangent, which is at right angles to that. So right angles leads to m for our tangent equals -1 over -3/4. So that's 4/3. Okay, so we're going to have a gradient of 4/3 at a point -1, 1. Right, and so we can find a line, we know its gradient, we know a point that it goes through. This is all pretty straightforward from here. So we go y minus 1 equals 4/3 x plus 1. That's just plugging in that point and that gradient. And then if we want to get it in y equals mx plus c form, we can go y equals 4/3 x. This is 4/3 plus 1, so plus 7/3. That's going to be the equation of our tangent there. Okay, show that the point 3, 3 lies on the circle. What is the equation of the point 3, 3? This we've actually already done in our sketch. If we go back to our sketch, 3, 3 was our point right at the top there, our maximal point. There it is. That's the tangent that goes through it. Now, we could go through the same process and it would work, but there's not really any need for this point because it's the very top of the circle. That means the tangent to it is going to be a straight horizontal line because this is a maximum point. If it's a straight horizontal line, then it's just going to have a fixed y value. And what will that y value be? It'll be 3. So part C we can do very, very quickly. So part C, it is C sketch. So it's definitely on the circle because it's just exactly 5 above the center point. And the tangent is just going to be y equals 3 because it's a nice horizontal line. Okay, the tangent drawn from the point 410 meets the circle at a point R. Calculate the length of TR. Okay, that's an interesting one. So here's our point 410. It's actually going to be somewhere up here. And so here's T 410. And it's going to hit our circle at a tangent. So it's actually 2 different possibilities here. It could either be this one here, bang, in which case R is, I don't know, somewhere around there. Or it could also be one that goes down this way and meets our circle somewhere over here. So there's actually 2 possibilities for R. It turns out though that the distance between T and those 2 possible R's is actually going to be the same, and that's due to some of the properties of circles. However, we can be even cleverer than that, because what we can notice is that if we draw a line from T to the center of the circle, well then we're going to have a radius, a tangent, and a hypotenuse forming a triangle, a right angle triangle, because the radius and the tangent are always at right angles. So the nice thing about that is then we can just work out the length of this side here from T to our midpoint of our circle, our center. We know the radial length, and we can use Pythagoras to find that distance. And we never even have to find the point R. So let's do that. Okay, so the line TC from T to our center is going to be the line that goes from 410 to 3, -2. So from 4 to 10 is going to be so the change in x values there is going to be 4 minus 3, and it's going to be, we're going to use Pythagoras, so 4 minus 3 squared plus, and the change in y values, we're going from 10 right down to -2, so that's going to be 10 minus -2 all squared. So this is 1 squared plus 12 squared equals 145. Alright, now you might think I should take the square root of that, but I'm actually just going to leave it squared because I know in the next little part I'm going to use it in squared form. Right, so we know we've got this triangle that kind of looks like this. This bit here is a radius, this bit here is TC, and this is the length that we actually want. Right, so we can say TC squared equals L squared plus R squared. Got a little right angle there. Pythagoras. Now TC squared is 145. R squared is 25. That's in the definition of this circle. So L squared is going to be equal to 120, and L equals square root of 120, which comes out to, so 120 is 4 times 30, so that's going to be square root of 4 is 2. times the square root of 30, and I don't think 30 has any other square factors, so that's about as far as we can go. Now, all that relied on you being able to see that there was a right angle triangle there, and I understand that that's not something that's necessarily obvious to you, at least not before now. Hopefully you'll be able to see that from now on. But there is an alternative way to approach this to find out what this line here is in the first place, what that tangent line is, and then we could go from there to find that distance. I'll show you that alternative way at the end of this video. Just in the interest of time, I might just finish up this video and then we'll keep going on that one. Okay, so part E is an almost identical problem. Let me quickly sketch a picture of that. Sorry, I cannot draw circles at the moment. So this, superficially, it seems like an identical problem. You could, of course, construct a right angle triangle, same as we did before. Bam, so there's our tangent that runs through this point here. We could find this distance here. We could call this, let's say that point's P, C. We could find PC, and we know the radius, and we could find that length there. But this one, a bit like part B before, part C, this one is a lot easier than it seems, because actually if we think about what is that point there that it's going to run through, that's actually, we're actually perfectly vertically below the far edge of the circle here. So the tangent is actually just going to be this perfectly vertical line running like this, and that point there is 8, -2, which was the right extreme of our circle anyway. So that means the equation of that line is just going to be x equals 8, and it's a vertical line. And how far is it from P to the intersection point? Well, it's just from -7 to -2, so the distance there is going to be 5. So that's going to be part E, I believe. The last part of this question wants us to find the intersection between the tangent that we found in part E, which was this one, that was x equals 8, and the very first tangent we found, which ran through the point -1, 1, which looked more like this, and it's just asking us to find that intersection point. If we know the lines that we have there, then this is a pretty straightforward process. This is just setting two lines equal to each other. So we have from E, we have x equals 8, and from B, we can go back and look on our previous pages. Y equals 4/3 x plus 7/3, and we're just going to let these two things intersect, so we're going to sub one into the other. So let's sub in x equals 8 into this, so we get y equals 4/3 of 8 plus 7/3 equals 32 plus 7 over 3 equals 39/3 equals 13. So y equals 13, and then how do we find the x value? Well, we just plug that back in. So we get 13 equals 4/3 x plus 7/3. I'm going to multiply through everything by 3 to make things a bit easier. 39 equals 4x plus 7. 4x equals 32. X equals 8. So our intersection is going to happen at 8:13. And we are done. Alright, so I said before there was an alternative way to approach part D. So just reminding you of what part D was. We had a point T which was 410, and we wanted to find the tangent that made with our circle, and then maybe find the point R where it meets the circle, and finally find the distance RT. Well, we can do that too. So I'm just going to go to Desmos, and I'm just going to show you quickly what this looks like. So we've got our circle here, and we've got this point that we're going to run through. Let me just make it a little bit easier to see. There we go. And we've got to construct a line that goes through this point. And first I'm just going to construct a line with any old gradient. So I'm just going to say y minus 4 equals x minus 10. Apologies, y minus 10 equals x minus 4. So that's a line that goes through the point 410, but it has a gradient of 1. We want a different gradient, so if I put a different gradient on that, let's say 2, then it still goes through 410, but it has a different gradient. But now it cuts through the circle. It's not quite right. So what we really want is sort of some unknown gradient, and then we want to be able to sort of slowly sort of modify that gradient and find the right value of m. And then that point there is going to be r. But of course there's another m that does the job, and that's this m here also constructs a tangent. So when we solve for m here, we should expect to get 2 answers. So we're going to find so what we're going to do is we're going to try and find the intersection between this line with some generalized m in it, between that line and this circle, and then from there we're going to solve for m to make this thing a tangent, and then we're expecting to get 2 solutions corresponding to these 2 possible tangents. So that means we get 2 possible r's. Here's our r value for this one. We get 2 possible values of r, but it's going to turn out that the length between this r and that point and this r and that point are actually the same by virtue of the right angle triangle argument that we made earlier. So let's do that. So let's try and find the equation of this green line here and this other line here when it's a tangent. Okay, it's kind of ugly, and when you do it, you're gonna realize that the Pythagoras way is really nice. So let's just remind ourselves of what that is. We have this point r. We don't know what it is, but we know that that's where the tangent is made. We realize that any tangent is always going to be right angled to a radius, and then we actually construct that hypotenuse there between the point at the center of our circle and the point we want our tangent to go through. And instead of finding this distance directly, which we called L, we found this distance here between our point and the center, which was called TC. And because we know those 2 points, that was much easier. But let's say you didn't think to do that, you didn't realize that these two were at right angles, and so you just had to construct this tangent and actually get the equation of that tangent. Alternatively, you might just get asked for the equation of that tangent, and this right angle Pythagoras method doesn't get you that equation. So we still do need to know how to find the tangent that goes through that 410. Now it's a bit of an ugly problem, but I'm going to show you how to do it. Okay, so the first thing is a tangent is just a special case of an intersection. Okay, so we have our 2 equations. This is just the general equation that runs through the point 410, and we have the equation of our circle. And to find an intersection, we sub one of them into the other. Now, it is going to get very, very ugly, so this would never be a tech-free problem. So what we're going to do is we're going to go to our CAS, and we're going to use the solve simultaneous equations problem, because that's how we do intersections. So, algebra, solve system of equations, 2 equations in x and y. Sweet. And the first one, of course, is going to be y equals some unknown m. Don't forget the multiplication sign here, because you don't want it to think it's a variable called mx. You want a variable called m and a different variable called x. X minus 4 plus 10. And our second equation, our second line, is we usually write y equals blah blah blah, but there's no reason you have to do that. You can just type it in as it is, x minus 3 all squared plus y plus 2 all squared equals 25. And then something horrendous is about to happen. Bam. Ugh. Right? So we get x equals this horrible expression in terms of m, because we don't know what m is. Like the intersection points are going to depend on m, right? So this is pretty horrible. So if you were just generally looking for the intersection points, this would be a terrible problem. But what we realize is that whenever we find an intersection between a line and a circle, we actually get we're going to get either 0 solutions, 1 solution, or 2 solutions. And what's our criteria for when we get exactly 1 solution, i.e. when we have a tangent? It's when that discriminant equals 0. So how can we see the discriminant in this expression here? Well, the discriminant, remember, is always the thing that's sitting under the square root. It's the thing that if that thing goes negative, then the whole solution won't exist. And if that solution's positive, then you get 2 nice solutions. But if that root is exactly 0, then that's when you only get 1 solution. That's when you get a tangent. Okay, so we're actually going to grab this here, and on a computer it's much easier. I can just copy. I don't know whether you can do that on your CAD's interface, but you can just type it out. So there we go. I'm just pasting it on there. And then I'm going to save that thing there as f of x. Oh, sorry, f of m. Right. And remember, I want this to be 0. So all I have to do is solve f of m equals 0 for m. And it gives me 2 solutions. Right, it gives me 2 different m's which do this job of making this little bit underneath the square root into 0, and therefore generating only a single little touching point tangent rather than a double cross or a complete miss. Alright, now that's a really subtle idea. I understand that's hard. Maybe go back, look at that again, where that's come from. But we're still not done. It's a really annoying problem, right? We have to take each of these. Remember, these are our gradients for our line. So we're going to take each of these and we're going to make a line out of each of them. So I'm going to grab that one there. And I'm going to write times, remember m was times x minus 4 plus 10. That was our equation of our line. Let me say, I'm going to save that one there as g of x. And I'm going to take this other one here, and I'm going to save that one, use that one as a gradient, and I'm going to save that one as h of x. And then I'm going to go to the graphing page, and I'm just going to have a look at what all this looks like. Okay, so let's make a graphing page, add graphs. And because I've saved it on the other page, I now don't have to enter it again. So I can just write f1 of x equals g of x. There it is. Use tab to bring that up again. f1 of x equals h of x. There we go. There's that one there. I'm just going to drag my screen around so I can see that. And I also want to put the circle on the page because I want to make sure that what I have here are some tangents. Now, you'll notice that this way of entering in is assuming that what we have here is a function. We don't have a function. We have a relationship. So what you need to do is if you hit backspace, then it actually brings up a bunch of options other than functions. So it brings up inequalities, but it also lets you just put in a general relation. So that's just going to let you put in any old equation. So here we can put in x minus 3 all squared and we hit enter, and it comes up on there. Okay, and look, those 2 lines that we've constructed are lovely tangent lines for that because we solved for the right m. And this point here where these 2 meet, I guarantee you that one there is going to be 410 because in the definition of those lines, that was the point that made them tick. Now, how do we find this point R that we're looking for in the first place, this intersection point? At this point, we can just use the analyze graph and find intersections. We're going to find the intersection between the circle and this line, and we get so we click one, we click the other, and then we make a box around the area that we want to look inside, and it finds it for us there. So that point there is negative 1.36. 0.447, and then you would use your distance formula to find the distance between that and 410. You could do the same with this one down here, but I guarantee you it would be the same distance. So I'm not going to bother. Okay, I'm actually not going to do that because we've already seen the answer in the previous problem. It's going to turn out to be 2 times the square root of 30. Or if you're using decimals, it's going to be some decimal approximation of that. Okay.